Good afternoon to you students. Today I'm going to discuss you on open cover and compact set. But before I start with that, let me begin with some basic definition. So these are not needed though, but we will use this definition of countable set. But but to understand countable set, you have to clear the definition of similar or equinumerous sets. So what is similar or equinumerous sets? Two sets A and B are said to be equinumerous or similar if there exists a 1-1 function f defined from A to B. If there exists a 1-1 onto function from A to B, then these two sets are said to be equinumerous, and symbolically we write A is similar to B. I hope it is clear by 1-1 on 2 function. Now finite set. What is a finite set? So far we have we define a finite set. A set contain a finite number of elements. Actually, that is just that is not the actual definition of finite sets. By finite sets, we mean that a set G is said to be finite if it is similar to the set of first and natural number. Means that if there exists a 1-1 onto function from G to the set of first and natural numbers, say up to n, then this set G is said to be a finite set. So this is the actual definition of finite set. It doesn't mean that it contains a finite number of elements. Such a set is called a finite set. If there exists a 1-1 onto function from G to the set of first and natural number, then G is called a finite set. Countable in finite sets. A set G is countably infinite if G is equivalent to the set of natural number. That is, if there exists a 1-1 onto function from G to the set of natural number, so such a set is called a countable infinite set. So here G, since it is a 1-1 onto there exists a 1-1 onto function from G to set n, then this G is called countable infinite set. Now next we come to countable sets. By countable set, a set G is said to be countable if it is equivalent, if it is either finite or it is countable infinite set. That is, if G is similar to the set 1 first and natural number, or G is similar to the set of natural number, such a set which is either finite or countable infinite is called a countable set. Now we come to the main definition we need in that we need later on. This is the definition of cover. What is meant by cover? You have a collection. F is the collection, this one. F collection of O alpha means F here is a set O1, O2, dash, dash, and so on. This F, this collection of F is said to be a covering or said to cover a set S. You have a set S subset of Rn, and this collection of F is said to cover S if this set S is completely contained in the union of this one, O1 union O2, that is, S is contained in O1 union O2 dash dash. So this collection F, the collection of all F, the collection of sets F, if their union contain this set S subset of Rn, then this collection F is called a cover of S. Now if each O alpha is open set, then this collection F is said to be an open covering of F. I'll discuss it afterwards. First, let us see the definition of cover. For example, you consider S to be the set of open interval 0, 0, 1, which is a subset of R. Now the collection F equal to set 1 by n, 2 by n, where n here varies from 1 to 3. That is 1. If you replace n by 1, you will have 1, 2 by 1 to another, from 2 onwards it starts, okay? 2, 3, 1 by 2, you have here 1 by 2, 2 by 2, that is 1. So you have 1 by 2 and open interval 1, 1 by 3, 2 by 3, 1 by 4, 2 by 4. If you replace n by 2, 3 and so on, then the union of all this contain this open interval 0, 1. So this collection of set 1 by n, that is 1 by 2, 2 by open interval 1 by 2, 2 by 1, 2 by 2, 1 by 3, 2 by 3, comma 1 by 4, 2 by 4 will form a cover of open interval 0, 1. But as we know that each open interval is an open set, so therefore this will form an open covering of this set S, that is open interval 0, 1. So we come to this definition of open cover. A collection of set F is equal to O alpha. Alpha belongs to indexing set I is set to cover as subset of Rn if S is contained in union O alpha. This is definition of cover. Now if each O alpha is open, then this collection F is called an open covering or open cover of set S. Now by definition of compact set, a subset S subset of Rn is said to be compact if every open cover, means this, in this case F forms an open cover of S, but if there exists a finite subcover of F which still covers S, that is, among this collection O alpha, alpha belong to the indexing set, a finite number of them, say O1, O union O2 up to On, their union still cover S, then this set S is said to be a compact set. If there exists a finite collection of F where each O alpha is open, then such that S is contained in union O alpha, alpha belong to N, then this set S is called a compact set. So this is a theorem we need. It is not so important, this theorem, but to prove Lindelof covering theorem, I need the result of this theorem. So here G is the collection of all countable collection. Means G here is either finite or countable in finite set. So G here is the collection of all open balls having center radii and center radius. That is, each of this A1 will be of this form. Open ball having center, whose center is a rational number and radius also is a rational number. So the collection of all those open ball having rational center and rational radii will belong to this set G. Now if X bar belong to Rn, if X bar is any element in Rn and S is an open set which contain this X bar, S is an open set which contain X bar, then there will exist at least one of this open ball having rational, at least one of this AI. What is this AI? It is an open ball having center radii, rational center and rational radii. There exists at least one of this which contain X bar and is contained in S. So what is the proof? Since S is open, as you know, an X bar belong to S implies that X bar is an interior point of S. So if it is an interior point, so there exists an open ball having centered at X bar and radius R such that that open ball is completely contained in S. Now let us write this X bar as ordered n tuples, say x1, x2, dash dash, xk is somewhere here, dash dash, xn. And let yk be a rational number such that the distance of yk from xk, where k here varies from 1, 2 up to n, is less than r by 4n, where r here is the radius of this open ball having centered at X bar and radius r. So as you can see here, this is an open ball having centered at X bar and radius r, whereas this is an open ball having centered at Y bar and radius q. I'll explain to you. So now we have chosen yk to be a rational number such that the distance of yk from this xk is less than r by 4n, and let y bar is a set of ordered n tuples whose entries are rational numbers, that is y1, y2, dash dash, yn, they are all rational numbers. Now the distance of y bar, let us take the distance of y bar from X bar, because here it is less than r by 4n, then we have here norm of y bar from, if you have X bar here, this Y bar is somewhere here, then the distance of Y bar from R bar is less than equal, because mod of Y1 minus, using triangle inequality, less than Y1 minus X1 plus Y2 minus X2 plus dash dash plus Xn minus Yn. But each of these, as we know that Yk minus Xk is less than R by 4n. So therefore, where k here varies from 1 to 3, so each of this is less than r by 4n, less than r by 4n. And how many terms are there? There are n terms, so you'll get nr by 4n. N and n cancel, you'll have r by 4. So this implies that the distance of this y bar from X bar is less than r by 4. Where r here is the radius, r by 2 is this half of the distance, and r by 4 is half of r by 2, say from here to here or from here to here. So the distance of y bar from X bar is strictly less than r by 4. Now let Q be any rational numbers lying between. Q here is a rational numbers. See, from here to here the distance is r by 4, and from here to here the distance is r by 2. So let us take Q to be a rational numbers lying between these two numbers, that is r by 4 and r by 2. So by a choice of y bar, because what is choice of y bar means that y bar here where each entry is less than, where each entry is a rational number. So by a choice of y and q bar, because we have taken q to be a rational number and y bar is also a set of ordered n tuples which belong to rational numbers. So this x bar, as you, if you draw now, you take the radius from here to here, q to be any rational numbers lying between this r by 4 and r by 2. With that measurement, take y bar as a center, draw a circle here having centered at y bar and radius from here to here. You will see that this point x bar is still inside this open ball having centered at y bar and radius q. But y bar, as you can see in the speaker, this open ball, it is inside this bx bar r. But bx bar r, because x bar being an open set, being an interior point, so this bx bar is contained in S. So this shows that by bar cubed is contained in bx bar r subset of S. That is, there exists an open ball. What is this open ball by cubed? Which contain x bar belong to this. So there exists an open ball having rational centers and rational radii which contain x bar. This is an open ball having rational center and rational radii which contain x bar. And this open ball by bar cube is nothing but one of this collection of G. That is, it can be A1, A2 or A3. So from this collection of countable n balls having rational and rational centers and rational xi, there exists at least one of them which contain this point x bar and is contained in S. I hope it is clear to you now, the proof of the theorem.